Over the past century, physicists have been fascinated by the concept of black holes. This concept began gaining traction around 1916. These cosmic anomalies are among the most captivating and enigmatic phenomena we know, sitting at the convergence of enormous gravitational forces and a profound disappearance from our understanding. A black hole potentially weighing as much as 2 to 4 million times the mass of our Sun continues to be an enigmatic presence. Despite decades of intense research, our understanding has expanded from almost no knowledge to piecing together more information. New discoveries have been made recently. Kaku's breakthrough has revealed startling insights about the interior of black holes that may challenge long-held beliefs and provide new perspectives on the nature of these celestial bodies. This new information opens the door to more in-depth investigations into what might have been overlooked until now. Come along with us as we move further into the fascinating world of black holes and discover what is concealed within the universe's vast and inspiring expanse. But what exactly are black holes? Before we examine the most recent findings by Kaku, it's essential to revisit the basic comprehension of black holes. While the vast majority of us have at least a general understanding of what a black hole is, there are still some key elements that remain unclear. In 1916, Albert Einstein's groundbreaking theory of general relativity predicted black holes. At the time, the concept was only theoretical. It wasn't until about 50 years later that evidence was discovered confirming that black holes are real objects in space. This revelation came in the 1960s during studies of the star Cygnus X-1, a luminous celestial body that emits X-rays. According to observations, these X-rays were not just moving at random but were being drawn into a dense, invisible mass. This mass was later determined to be a black hole. The discovery changed our perception of the cosmos. It was monumental, demonstrating that black holes were not figments of Einstein's imagination but tangible, elusive entities that warranted further investigation. Following this groundbreaking discovery, scientists worldwide began a global quest to learn more about black holes. Their efforts resulted in the discovery that the Milky Way alone may contain approximately 100 million black holes. However, due to the difficulty in identifying them, this estimate remains imprecise. Even though black holes are incredibly difficult to pinpoint, scientists think that millions of these massive entities are hidden within our galaxy, making it even more important to comprehend them. Let's dissect the fundamental idea of gravity. So much force is exerted by black holes that anything getting into their territory is subject to extreme gravitational pull. The singularity is the point at which the rules of physics as we know them cease to function. In other words, black holes are like enormous vacuum cleaners, pulling everything into them. One of the most terrifying aspects of studying black holes is that if someone were to fall into one, they would gradually stretch out and become a singularity themselves, their bodies shattered by the ferocious forces of gravity before the point of total destruction. It's best to avoid getting too close to one. Though they are scattered across the universe, the nearest black hole is nearly 500 light-years away. Despite this distance, their presence raises legitimate concerns. In 2021, scientists achieved a significant milestone, capturing the first clear image of a black hole, the M87 black hole. This achievement was the result of numerous nights spent taking photographs and aligning them to create a single, cohesive image. As more data was gathered, researchers discerned that black holes consist of 3 distinct layers, contrary to the common misconception that they have no limits. The first of these layers is known as the event horizon, which identifies the point beyond which nothing can escape. When something crosses this line, it is inevitably drawn toward the black hole. The second layer, known as the photon sphere, is where light becomes trapped, unable to escape due to the powerful gravitational forces at work. The final point is the singularity, where all matter is compressed into an infinitely small point, a place where the very fabric of reality collapses and the known laws of physics break down. Even more fascinating is the fact that each black hole is unique in its own right. While they generally adhere to the 3-layer structure, their behavior can vary significantly. This makes them especially difficult to study, as conventional scientific methods don't apply. Scientists have no choice but to examine these anomalies by indirect means, such as observing the radiation they emit or analyzing the gas and dust circling them. Sending a probe directly into a black hole is an ineffective exercise, as anything that crosses the event horizon is inevitably pulled toward the singularity, where it is crushed into nothingness. This unavoidable fate means that billions of dollars cannot be spent on investigations that would ultimately fail to yield valuable data. Consequently, researchers are left to study black holes in 2 dimensions, despite their 3-dimensional structure. Adding to the complexity of black hole research is the fact that no 2 black holes are identical. When studying them, we must account for the breakdown of physics as we know it. Theories about the origins of black holes suggest that they may form when massive stars collapse in on themselves. As a star exhausts its fuel, it can no longer produce enough energy to counterbalance the inward pull of gravity, leading to its eventual collapse into a black hole. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. To further understand the nature of black holes, NASA scientists turn their attention to the center of the universe, particularly the M87 galaxy. There they observed a massive whirlpool of hydrogen gas spinning at a stupendous rate, speeds of 1.2 million miles per hour. The centrifugal force should have caused this gas to fly apart, but instead it remained intact, suggesting the presence of a massive object at the center, likely a black hole. This object is believed to weigh 3 billion times more than the mass of our Sun. Another significant theory was proposed in 1963 by New Zealand mathematician Roy Kerr, who used Einstein's equations to describe the behavior of rotating black holes. He argued that black holes don't necessarily collapse into a single point. Instead, a rotating black hole forms a structure known as a thin ring, called the ergosphere. This rotating disk of matter is key to understanding the disintegration of physical laws near black holes. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that could provide a shortcut through spacetime, connecting distant parts of the universe or even parallel universes. To grasp the idea of a wormhole, it's important to understand the concept of spacetime. In the mind-bending explanation by Michio Kaku, spacetime is described as a warped, 4-dimensional fabric shaped by objects with mass. This warping creates gravitational fields that influence the movement of other objects. Consider spacetime to be a piece of paper. If you fold the paper, you create a shortcut between 2 points. This shortcut is the essence of a wormhole, a spacetime traversal that could connect distant locations almost instantly. Despite the fact that wormholes are a theoretical idea without any direct evidence that they exist, they are a natural outcome of general relativity. However, wormholes are inherently unstable, meaning they would quickly collapse if constructed. Despite this, the concept of a potential wormhole gateway to different parts of the universe, or even different points in time, has captured the imagination of physicists for a long time. One particular kind of wormhole, known as the CR wormhole, has been a subject of fascination. Named after Royer, this hypothetical wormhole could theoretically connect 2 distant points in spacetime, possibly even linking different timelines or universes. At the same time, while the idea of using wormholes for interstellar or time travel is exciting, there are significant challenges to overcome. Wormholes are anticipated to be unstable, and the extreme radiation and forces surrounding them would make it nearly impossible to traverse them safely. Critics argue that Einstein's equations, while useful for understanding gravity, do not account for the quantum forces that govern radiation and subatomic particles. To truly understand black holes and wormholes, a new theory is needed, one that unifies gravity with the theory of quantum mechanics. Frequently, this theory is called the theory of everything. It is a quest pursued by numerous physicists, including scientist M. Yakubu, for years. One promising candidate for this theory is superstring theory, which suggests that subatomic particles are actually tiny vibrating strings. The theory proposes that these strings create the universe's fabric, not only explaining gravity but also the phenomena surrounding black holes and wormholes. Superstring theory also requires the existence of extra dimensions of spacetime that are so small they are impossible to detect with current technology. Despite the challenges, the pursuit of understanding black holes, wormholes, and the fabric of spacetime continues to captivate scientists, offering the potential for revolutionary discoveries that could alter our perception of the universe. Expanding from our current location, The pursuit of superstring theory and other theories that aim to unify nature's forces is an ongoing challenge, but it holds the promise of unlocking new insights into the very nature of reality itself. These theories propose that the universe is composed of more than the familiar three dimensions of time and space. In point of fact, they suggest that additional dimensions exist, but they are so minuscule and compact that they are beyond our observation directly with the technology of today. However, their existence may hold the answer to understanding phenomena like black holes, wormholes, and the deepest mysteries of the cosmos. Superstring theory offers a fascinating picture of the universe, proposing that all matter and forces are manifestations of tiny strings that vibrate. These strings can vibrate at different frequencies, with each vibration corresponding to a different particle, just as a guitar string can produce different notes depending on how it vibrates. The fundamental particles of nature might correspond to different vibrational patterns of superstrings. If proven, this theory would not only provide an all-encompassing explanation for the fundamental natural forces, like gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, but also open up entirely new ways of understanding the universe's structure. This could potentially provide answers to some of the most pressing concerns in physics, including the nature of dark matter and dark energy, which together account for a vast majority of the universe's mass and energy but remain largely unknown. Despite the fact that it is super elegant and promising, superstring theory remains unproven. One of the major obstacles to testing the theory is the fact that the extra dimensions it predicts are so minuscule that they are beyond our current observational capabilities. Detecting these dimensions would require instruments of unprecedented precision and sensitivity, and even then, the evidence might be indirect. This makes superstring theory a difficult subject to study or test with traditional scientific methods. Yet, its mathematical beauty and coherence make it one of the most compelling ideas in theoretical physics. Simultaneously, scientists are working on other approaches that might lead to breakthroughs in our understanding of quantum gravity. For example, the study of black holes is another field of research that seeks to combine the principles of quantum mechanics, which govern the behavior of subatomic particles, with a theory of general relativity, which explains the behavior of massive objects such as planets and stars. The hope is that by merging these two theories, scientists can gain a clearer understanding of how gravity works on the quantum level and, in turn, gain deeper insights into the nature of black holes and other cosmic phenomena where quantum mechanics meets general relativity. This is especially crucial when studying black holes as a result of the extreme circumstances near the event horizon of a black hole, where gravity exerts a tremendous amount of force. These conditions demand a theory that can account for both quantum effects and relativistic effects. In fact, the interior of a black hole, where the singularity exists, is one of the most perplexing and bizarre environments in the universe. The singularity represents a point where space and time become so warped that the usual physical laws break down. Understanding what happens in such a place requires a theory that can reconcile quantum mechanics and general relativity, which has resulted in the development of ideas like loop quantum gravity and other quantum gravity models. These aim to resolve these contradictions and provide a more complete illustration of black holes. As we continue to probe the mysteries of black holes, one thing is certain. The more we learn, the more we comprehend the extent of what is still to be discovered. Black holes are not just points of destruction but are also places of incredible complexity and potential. Whether they are gateways to other dimensions, according to some theorists, or whether they hold the key to understanding the deepest secrets of space and time, black holes remain a crucial area of study. As our tools and theories evolve, so too will our understanding of these enigmatic objects. Focusing on the upcoming major obstacle, it will be to refine our methods of observing and studying black holes. One of the most exciting advancements in recent years has been the development of gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by the movement of massive objects, like the merging of black holes. By detecting and analyzing these waves, scientists can study the behavior of black holes and other celestial objects in ways that were previously unattainable. Already, the identification of gravitational waves has provided groundbreaking insights into the dynamics of black hole mergers, and future experiments are likely to yield even more information. In addition to gravitational waves, another promising area of research involves the use of advanced telescopes and imaging techniques. The Event Horizon Telescope (EHT), which produced the first image of a black hole in the M87 galaxy, is an example of how innovative technology can shed new light on black holes. By combining information from several radio telescopes around the world, the EHT was able to capture an image of the black hole's shadow, offering a glimpse into one of the most mysterious phenomena in the universe. As technology continues to improve, it's likely that we will be able to observe black holes in even greater detail, revealing more about their structure, behavior, and role in the cosmos. The study of black holes is not just about understanding these strange objects in isolation. It is also about understanding the fundamental workings of the universe. Black holes are crucial to our understanding of space-time, gravity, and the very nature of reality. By studying them, we are not only learning more about these objects themselves but also about the laws that govern the universe at its most extreme scales. In conclusion, the study of black holes is among the most thrilling and challenging fields in modern physics. With each new discovery, we inch closer to unraveling the mysteries of these cosmic giants. Through the research of gravitational waves, advancements in imaging technology, or the emergence of brand-new hypotheses, black holes continue to captivate the imagination of scientists and laypeople alike. As we investigate these most extreme and mysterious objects, we are compelled to answer fundamental questions about the nature of spacetime and existence itself. In doing so, we may be nearing the point where some of the most important secrets of the universe are revealed, possibly even obtaining responses to questions that have eluded humanity for millennia.